Hello, welcome. So, in the previous episodes in this series, I've been building an FPGA stack machine CPU from scratch. So far, we have a stack that's able to push and pop values. We've got an ALU in quotes because this is just an adder for now, but it will do. And that's able to calculate an addition from the top two values on the stack. And then it's able to store it back onto the stack. And we've got some program memory, program counter, and a bit of an assembler here to allow us to assemble simple programs. I think in this episode, I'm going to jump right into getting the microcode working because, it just makes life easier. So without further ado on that, customasm is the program I prefer for building these sorts of things. There's a lot of documentation. I believe it's in the wiki. Yes. So there's some documentation on how this tool works. This is an amazing contribution to hobbyists everywhere. It just allows you to skip having to build an assembler for your CPU for a very long time. There's some limitations, but honestly, you can get a surprisingly long ways just with this program. It's written in Rust, so it's really easy to install. It works on every platform. There's even a web version of it. So if you don't want to install anything, you can just use this web version and it'll work just fine. There's some limitations, but yeah, you don't even have to install anything to use this program. So I highly recommend it. Therez a link in the description for it. But it's just github.com/hlorenzi/customasm. And yeah, if you really enjoy this project, I would highly recommend considering sending a few bucks his way, which actually I think I may do because I've used this program a lot. So yeah, I'm definitely going to send a few bucks, probably to his Ko-fi because that's going to have the least fees. I think Patreon takes a bigger cut, but yeah, anyway. It allows you to basically do some rule defs that kind of describe the machine language of your processor, or in this case, of your microcode. And then you can just use it right away. So, and it's got a lot of nice debugging output. So if you're getting weird results, you can figure it out pretty easily. So that is awesome. And it also handles variable length instructions where you might have the same instruction, but it has a few different lengths for like higher precision immediates and things like that. So it can handle that as well, which makes it very, very powerful. So highly recommend it. Anyway, I've done enough sales pitch on this. I'm sure you're sold already. So let's kind of just dive into it. Yes, I'm going to just do some on-screen coding. I hope that's okay. Let's just make it a little larger. And we don't need the file browser here. I wish asking GitHub Copilot would help. I guess we could try it. What do we want to ask Copilot? Right, the scaffolding for using that will not work. I don't think that's going to work. Let's try. you never know. What are we going to do to get the, that's not what I want. I guess I got to save it first. Yeah, I didn't think so. It's confused. I'm not even going to go there because it's just a waste of time. When AI is awesome, it'll be quite awesome. I'm not one of those doomsayers that says, oh, AI is going to take my job. There's no way you can replace a human. Not yet, anyway. The big problem is that AIs don't have any work experience. They have world smarts. They're book smart. Sometimes it's helpful. Most of the time it's not. And sometimes it's so close, but then so subtly wrong. And it just makes, anyway. So don't worry about AI taking your job. Worry about not using AI to accelerate your current job, because it can make you more productive. And if you get used to like how it makes mistakes and stuff, it can speed things up. It just makes you more of a code reviewer rather than a programmer, which is annoying, but at the same time, it's a good skill to have. So, if you're used to catching AI's mistakes, you'll catch a lot more mistakes, just in general. So anyway, where do we start? Got a blank file. Well, I believe, you know what? Honestly, what I usually do is I copy and paste from something else. So let me kind of take the microcode from some other project that I've got. Okay, this is the microcode from another project that I have. I'm just going to clean this up a little bit because there's a lot of stuff in here that we don't need yet. We'll probably use that. We'll use the bank, I think. And then kind of some examples of a couple of instructions would be nice. Okay. The size, I'm not sure yet, but and the bits right now is just 8. So let's just use that. So what do we've got in our, we have the 0 bit is push. The 1 bit is pop. And then we have I to toss, NOS to toss, and Y to toss. We might fix that in a little bit, but let's just get this working. We have I, and that's basically it. So let's see if I can go off memory here. Actually, you know what? I got an idea. I'm just going to make a screenshot of this. And then I can keep the screenshot open while I'm working here. I think it'll stay on top. Come on, resize. Nope, that's as small as it gets. Okay, well, that'll have to do. Okay, so we've got push. That is the 0th bit. And then the first bit is, this should be a 1, 0th bit, first bit. Yeah. This is pop. Our rules. Well, let's just get all of the bits. We've got NOS, toss, and this is where AI can be handy because it's helping me fill some of this stuff out. Y, toss, because it's figured out the pattern now, so it's doing well. And then we've got I. Let's call this M. It's basically there, but it's probably better to make that just a field on our instructions. So currently we don't have like a done instruction. So, and then it's using 4 spaces. 4 spaces is probably fine. Let's just leave it at that. Okay, so I don't think I need this anymore. Well, maybe. Yeah, let's just leave it for now. So we've got, let's just call it op for now, because I don't have a better name for it. We don't have busy or any of this other stuff. So it's a 3-bit op, I think. And that's in the upper bits. So we have to shift that. We shift it by 5. So maybe we could have shift being 5. And then we've got flags. I guess. And flags is 5 bits. I think, yeah, well, we might have to adjust this, but that looks good for now. Our bank def, I think, is fine. And then we might be able to actually just do some, okay, I think done with that. Might be able to do just some, oh, I need flags in here. Eventually this is not going to be like assembly. It's going to be microcode. So the position of the microcode will matter. So at each address, we would have whatever the input bits into the microcode ROM would be, with the output bits being whatever the instruction is. So actually, let's just do it that way. So what instructions do we want right now? Well, we've got push. So let's just do push. Like that, basically. This jump is not useful. So we would have push with some sort of immediate, I guess. Or wait, no, this would be load immediate, wouldn't it? So when we're loading an immediate, we have the push line high. We have I to toss. I think that's it. I guess we need a way to set the top of stack. Should that be load immediate? No. Definitely want that to be a push. So I guess we can do without that instruction. Okay, so, and then we've got add. Add, we would add is pop and Y to toss. Yeah, and then we wouldn't have an immediate in here at all. So we could probably remove that. Yeah, do we want to just assemble in microcode, or do we want to do the actual microcode? Yeah, we'll just do the actual microcode, so then there's no immediates, because that is not necessary. So it's always just flags, and 8 bits of it, I guess. So we can simplify this a little bit here. I guess these are the only instructions that we have. I'm trying to think. I guess we've got drop. Comma 0 isn't necessary. We have, oh, nop, of course. drop, dupe. Dupe is a push of nos to toss, I think. I think that's all of the instructions that we currently have implemented. Let's just assemble that. Well, actually, let's put it in the dig. And then I think we have to specify, or no, I think it's a -O on that. And then we've got -F, logism8, I think. Bank def. Saved it. Okay, what's it not like? Oh, I forgot to remove that. That would be why. Okay, it appears to have worked. Let's just, I forget, I think it's hex. Annotated bin, I think. What? Oh. Okay, so we've got our NOP, we've got push, pop, or no, we've got NOP, load immediate. Yeah, I think that's good. The address looks correct. Yep. Actually, it might be handy to just keep that file, so I think I will. Yeah, let's run with this. So what do we need to do to implement that microcode? Well, let's move some things out of the way here. It would essentially be a ROM right here. So let's put a ROM there. And I'm just going to be silent for a moment and do the changes in here. Okay, so we now have microcode that's getting the microcode bits, and we've got a program. The program is now 16 bits. So now we can store a full-sized immediate if we want to. And in the future, we can have different instruction encodings so that instructions that don't take an immediate won't have them. But for now, it'll always have them. And we could store a program in there to test out the microcode. But we'll have to store the program as hex. So why don't we just go and make another custom ASM to essentially be the assembler for this CPU. So might as well get all of the custom ASM stuff out in this episode. So there we go. So what I'd like to do is set up a CPU def.asm and have that basically have the rule defs for each instruction in it. So I'll just copy this, I guess. The LE here means little endian. I don't think we need that if we have a bank def that says that it's 16 bits. So actually, let's grab the bank def as well. So this will be 16 bits. The size, I don't really know, but that's probably fine. And the blue squigglies are just a spell checker. So let me just turn that off. I guess. I don't really want, yeah, whatever. I'll just put a, there. I think that's basically what we want. An op is going to be opcode immediate. I think you can just do that, like that. The opcode is in the lower 8 bits, though. And what do we got? We have NOP. I think this is the macro syntax here. Guess we'll see in a moment. Okay, we've got NOP, load immediate, add, drop, and dupe. I think you can do this. And then this can be, I think these need to be capitalized probably to make them different. Not sure. Let's see if this works. And then we've got our first program. Let's load 1, load 2, add, load 4, add. Let's see if that works. And normally the program wouldn't be in the CPU def, but we'll just do that for now. I forget how to make it dump to standard out. -o dash, maybe? -p, okay. Okay. That would be why. And I think you have to do this. Why would that be? That doesn't look right. This shouldn't be 2. Or it is. It should be 2. Then this shouldn't be 2. Why is the 0 not showing? Let's just line these up. maybe it does the right thing with logism. It does not. Shouldn't need to do this, but let me try. No. Let's try making these uppercase. Let me just pause here for a second and see if I can figure out exactly what's wrong. It is currently dropping the 0 from some of these instructions. And I don't know why. It shouldn't. I mean, I suppose what we could do is put the opcode in the upper, and these curly braces shouldn't be necessary. They're only necessary in the ASM blocks. So it should be this. Let's try swapping these around and see if that works. Yeah, I'll be back as soon as I figure this out. Okay, I figured it out. This doesn't need to be a separate rule def. This needs to be called subrule def. Otherwise, for some reason, this was being taken as higher precedence, I guess. Yeah, whoops. Okay, so subrule def, and then you can give it a name, and then that can be the type of a parameter. And then you've got this little endian is not necessary, and this 16 is not necessary either. And then I was just trying out all of the instructions. So yeah, now it's working. They're putting the 0, 0 there where they're supposed to. So that is good. We've got definitions of all of the instructions, and I'm going to just remove these because I don't need them. Okay, so we've got a program that we can make. So I'm just going to produce logism 16 format, and then that's the output. Okay. Okay. I think that might work. 8 bits found here. My cat wants out. You just want it in. Okay, so this is 16. Oh. Okay, it seems to be working. It is wanting to push 1 onto toss, which happens, and then 2, that looks like it worked, and then it should add, so it'll pop the 1 off and put Y into the top of stack, which it does, and then it should push 4 onto the stack, which it does, and then it's done with 7 on the top of stack. Okay, that looks like it worked. Awesome. Yeah, that worked. Cool. Okay, I think that's it for this episode. We have a microcode assembler going, and we also have a proper assembler. So we can assemble programs and put them into the program memory. I think this is a good amount of work for this episode. So yeah, thank you very much for watching. There are links in the description for this program. You can find it by Googling H. Neiman and digital, but there's also a link in the description. There's a link in the description for the GitHub repo for this project. Each episode has its own commit. So if you just look through the commits, you can find the one for this episode and get the digital files and play around with them. I highly recommend that because it's a great way to learn. And yeah, you can also get the custom ASM and play around with it. I didn't do a lot of explanation into custom ASM. I don't know if I'll have time to do like a full tutorial, but I'm hoping the documentation is good enough. Also in the description is links if you're feeling generous. No obligation, but it does help out. Unfortunately, advertising, like the ads on these videos don't pay me very much, and neither does premium. So yeah, I'm just too small, and to be honest, I don't think I'll ever grow big enough that the ads can support me. So yeah. So yeah, thank you very much for watching, and I hope you have a great day. Bye.